In this video, we will discuss the problem of model generalization and the bias-variance trade-off. The bias-variance trade-off is one of the most fundamental results in machine learning. Having a good understanding of the bias-variance trade-off is crucial for the good design of machine learning algorithms. So what is model generalization? In a machine learning problem, we always try to generalize the known dependent variable on seen instances to unseen instances. What do we mean by unseen instances? What it means is that that particular pair of the features and dependent variable was not included in the training data. So in most applications, it makes sense that what you will always be trying to predict will not be included in the training data. So for example, you might have training images with seen labels, but you'll always try to label an unseen image, an image that was not included in the training data. Or for example, in a spam detection application, you could be given training emails labeled as spam or non-spam, and then when you have a new email coming in, you will try to label an unseen email. So this email was not included in the training data. Now, one important aspect that once you train a model is that the classification accuracy on instances used to train a model is usually higher than that on unseen instances. So what do I mean by that? So whatever instances you use to train your model, you could also try to predict them at inference time. And the accuracy that you get if you try to predict those same instances that you used in the training data would always be an optimistic estimate of the true accuracy that you will get when you pass unseen instances that were not included in the training data in your model. Now obviously, in any real application, there is no use of really predicting the instances for which you already have labels again. So we only really care about the accuracy on unseen data, which is referred to as the generalization accuracy of the model. So let me distinguish at this point about the difference in memorization and generalization. Machine learning models are capable of both memorization and generalization. So why is the accuracy on the seen data higher? The reason for this is that the trained model remembers some of the irrelevant nuances in your training data. So these might be nuances which are not really relevant for predicting the true dependent variable on the unseen data. So there are certain circumstances where the model is more likely to remember irrelevant nuances. So the question arises, under what circumstances is the gap between the seen and unseen accuracy likely to be high? So there are two particular circumstances in which the gap between the seen and unseen accuracy is high. One is when the amount of data is limited. In that case, the gap between the seen and unseen accuracy tends to be high. The second is that when the model is complex. So when a model is complex, it has higher capacity to remember these irrelevant nuances. And the combination of these two characteristics often turns out to be a deadly cocktail. And when you have a high accuracy gap between the predictions on seen data and the predictions on unseen data, this is referred to as overfitting. Obviously, overfitting is an undesirable characteristic of a machine learning model. So in order to understand this point, we will visit an example of curve fitting. So imagine that you just have two variables, an independent variable x and a dependent variable y. You're trying to predict the value of the dependent variable y from the independent variable x. So you have some training data containing pairs x, y, and then you use these training pairs x, y to fit a curve. So y is equal to some polynomial of x, and then that is used for unseen instances. So then you give it a value of x in order to predict y. So in this case, you can see that the curve that passes through these instances, it's a nonlinear curve. So it would seem at first impression, the first impression would be that a polynomial model such as a fourth order polynomial might be better in this case than a linear model, because a linear model would simply be a simplification. So I've shown both the true model, which is obviously some kind of polynomial fit to the data points tends to be better than the linear simplification. Linear simplification also gives you a reasonable accuracy, but obviously at certain points it will always be inaccurate. So for example, at x is equal to 2, the linear model will almost always overestimate the true value of the dependent variable. So it will almost always predict a higher value of y than the true value. So that is like a kind of like what you call a bias of the model. So we will discuss this term a little bit more formally later. Now, even though it might seem at first sight that in this case a polynomial model is better than a linear model, the surprising result, and this is the key point in understanding the bias variance trade-off, is that it is not necessarily true that you will always do better with the polynomial model as compared to the linear model, because according to the bias variance trade-off, depending on how much data you have in this setting, if you have a small finite data set, you might actually do better with the linear simplification than with the true model. So in order to understand this point, we will look at a degenerate case where you have a very small training data set, a very small training data set of 5 points. So here I have shown 3 examples of training data sets with 5 points. So it's the lower left, the lower right, and the upper right. So I have sampled 3 different training sets, and for each case I'm trying to predict the value at x is equal to 2. And now in this case, what happens is that when you have a particular sample of 5 training points, it's actually possible to fit a polynomial curve of degree 4, because that has 5 parameters, exactly through these points. So in this case, what happens is that you get 0 error on the training data, because the polynomial curve passes through all of the points, because it's a 4th order polynomial, and including the constant value, you have 5 parameters and you have 5 points, and you can actually draw a polynomial of order 4 exactly through the points. But it turns out that when you have different training data sets, if you vary your choice of training data set, you will get very different curves. So you can see that, for example, the curve on the upper right and lower right, the 2 models that you get on the upper right and the lower right, the predictions that you get at x is equal to 2 are drastically different. So here you have a different problem, that you have a variation in the predicted value over different choices of training data sets. This is what is called the model variance. And the problem is that when you're looking at the overall error of a model, when you're working with a finite data set, it isn't just the bias that you have to be worried about. It isn't just the inherent problem caused by the simplification, which I showed in this chart. It is also the problem caused by the variation in your choice of training data set. Your choice of training data will have some irrelevant nuances which will be reflected in the model, which will give you an inaccurate prediction. So for example, if you look at the model on the upper right, it has some irrelevant nuances because of which the prediction at x is equal to 2 is much higher than the true value of the prediction at x equal to 2. So in general, these are the observations from our example. That is, a higher order model is more complex than the linear model, but it has less bias. But it has more parameters. So what happens is that for a small training data set, the learned parameters will be more sensitive to the nuances of the data set. And different training data sets will provide different predictions, because they will learn completely different parameters for y at a particular x. And this variation in the prediction of the same value of x is referred to as model variance. So here you can see at x is equal to 2, you will be your predictions will be wildly different. And neural networks are inherently low bias and high variance learners. And in fact, one of the reasons why neural networks did not work in the early years is that we didn't have enough data. And often the overall error tended to be high because of the contribution of this variance component. So we always need ways of handling complexity. So this particular chapter and the corresponding series of lectures will be talking about the various ways in which we ensure that the model generalizes better to unseen data. Now, aside from the bias and variance, we have a noise component. So unlike bias and variance, the noise is a property of the data rather than a property of the model. So noise essentially it refers to unexplained variations of the data from the true model. So let's say you have a true model of the data fxi. Let's say there was some oracle that gave you the true model, which is fxi, but there'll still be some error remaining. And this does happen in the real world. So for example, if a human mislabels a test instance, so for example, if you have an image and you mislabel it, even if you build an ideal model, you can never predict it accurately. And similarly, if you have sensors collecting your data, and let's say a sensor malfunctions that it makes an error during the collection of temperature, you basically cannot do anything about this, even if your seeded knowledge about what is the true model. So this kind of error, which is a property of the data, it shows up as what is called the Bayes error rate, Bayes optimal error rate. So now let's set up the bias variance trade-off, a little bit of a more formal treatment. So imagine that you are given the true distribution B of the training data, and you have a principled way of sampling training data sets from the training distribution. So you're given the true. Now this is like an oracle. Imagine if you had a true distribution of training data, it's like giving you infinite data. This is an ideal situation which never happens in the real world. Because it doesn't happen in the real world, because you always work with finite data, that's where the variance comes from. But just imagine, for the purpose of setting up this bias variance trade-off, that you were actually given the true distribution of training data, and you have a principled way of sampling data sets from this training distribution. And imagine that you create an infinite number of training data sets and trained models by repeated sampling. So you have this principled way of sampling data sets, and you create many different training data, and for each of these training data sets, you are creating a different trained model. So just to go back a few slides, so here, for example, you are sampling 5 training points from each model, and you're creating a different training model in each case. So that's exactly what you're doing over here when you're setting up the bias variance trade-off. And now imagine you have a fixed set T of unlabeled test instances. So in that example I showed you earlier, that x equal 2 was an example of a test instance. So here you're only given the feature value, so there's some fixed set T. It's a large set T, let's say, of test instances. And this test set T does not change over different training sets. So when I showed you the example before, we were trying to always predict that x is equal to 2. For the various trained models, we were always trying to, so it's x equal to 2 is like a test instance, and we are trying to predict it over every trained model. So here we have a fixed set T. Assume you have a very large set T of unlabeled test instance, and what you're going to do is that you're going to compute the prediction of each instance in T for each trained model. So what is an informal definition of bias? So what we'll do is that we'll compute the average prediction of each test instance X over the different training models. So here you have this set T of test instances, and for each of these test instances, you're going to compute the prediction over different training models, and then you can always average these predictions in order to give you a more robust prediction. So for example, if you go back to this example over here, these different predictions at x equal to 2, the different prediction of y at x equal to 2, you can average them, which will give you a more robust prediction. So the point really here is that even after you average them and get a more robust prediction, the average prediction of the test instance will be different from the true unknown model fx. And this difference between the averaged value, this robust value of the prediction and fx is caused by the erroneous assumption simplification in the modeling. So for example, if you chose a linear model, you chose a linear simplification to a polynomial model, no matter what you do, you will always estimate no matter how much data you had, you would always have some inaccuracy. So now, if for example your true unknown, so if you had an infinite amount of data, and and in this case, because your training distribution, you can generate data sets with an infinite amount of data. If the true unknown model is an order 4 polynomial or higher, and we used any order 4 polynomial greater in GX, the bias would be 0. So as you move towards higher levels of complexity, you can reduce your level of bias. Now, what is the definition of variance? Now, this model that you're using, this GXD, note that this GXD is a function of the typical data set D, because the model is built using the specific data set. Now, and it's a prediction, G, for a specific X and a specific data set, you have a prediction which could be different with the data set D. So now you could, for a fixed X, if you vary D, your prediction is going to vary. So just to give you an example, if we go back to this slide over here, if you fix X equal to 2 and you vary the data set, so you have you have 3 different training data sets of 5 points, your prediction GXD for each of these data sets is going to be different. So now, obviously all of these predictions, they cannot be simultaneously correct, and this variation itself contributes to the error, because the prediction of the same test instance will be different over different trained model. So the variance of GXT over different trained model is known as the model variance. So in our previous example of the polynomial fitting, the linear model will have low variance. So for a small number of data points, you will pretty much get a similar kind of linear line, whereas the higher order model, you will get very different polynomial curves, as we saw in our previous slides. So the higher order model will have high variance. So what does the bias variance equation say? The bias variance equation says let EMSE be the expected mean squared error of the predictions of the fixed set of tests instead of the different samples of training data sets. Now here we are of course assuming that your dependent variable y is a real value. You also have versions of this which work for discrete values, but for simplicity, let's just discuss real values for now. So your EMSE, which is your mean square error, is equal to bias square plus variance plus noise, and a proof of this is given in the book. And what happens is that different types of models, different components will contribute more. So in linear models, the bias component will contribute more to this error, whereas in polynomial models, the variance component will contribute more. So we have a trade-off when it comes to choosing model complexity. You will not always do better with a more complex model, or you will not always do better with a simpler model. It depends on the kind of situation you have, the amount of data. So many factors go into this. So here, I have shown an example of a curve showing the bias variance trade-off, where I have squared error on the y-axis and I have the model complexity on the x-axis. So as you can see, as the model complexity increases, the bias reduces. So in our previous example, for example, for a polynomial curve fitting, as you increase the order of the polynomial you're using to fit the training data, the bias will keep reducing. Assuming that your true model is indeed a polynomial model. And similarly, you can see the variance keeps increasing. For higher order polynomials, you will have higher variance, and the overall error over MSE is going to be the sum of these two quantities. And then of course you always have the noise component, but right now we are just looking at the bias and the variance, their effect. And there will be a point of optimal complexity. So there will be a point at which you will get the best possible error. That depends on several factors, including the amount of data that you have. So what is the key takeaway of the bias variance trade-off? The key takeaway is that a model with greater complexity might be theoretically more accurate if you had infinite data, because it has low bias. But you have less control on what it might predict on a tiny training data sets. And different training data sets will result in widely varying predictions of the same test instance. And some of these must be wrong. And that is really the contribution of model variance. So the key takeaway is that a more accurate model, a more accurate theoretical model for infinite data is not a more accurate model for finite data. If you had to summarize the key takeaway of the bias variance trade-off is that you should not use a sledgehammer to swat a fly. So how does this all apply to neural networks? So the recent success of neural networks is made possible by increased data. So large data sets, they help in generalization. And in fact, during the early years, one of the reasons why neural networks didn't work very well is because we just didn't have enough data. Now, how you design your neural network has a direct effect on its generalization. So for example, if you have a neural network, you increase the number of hidden units, intermediate layer, it tends to increase the complexity. And if you increase the depth, it often helps in reducing the number of units in hidden layers. So typically if you have depth with nonlinearity in the hidden layers, it tends to help generalizing better with fewer units. So in some sense, there are some design choice involved, because when you increase the depth, then you have problems with convergence, which indirectly leads to increased bias. So here there's always an issue of what are the proper design choices to use to reduce overfitting in complex models. And sometimes it is better to use and in fact often it is better to use more complex models with appropriate design choices. So if you can have the design choices right, it's better to use a larger network. Just reducing the size of neural network upfront will result in inflexible models. So it's better to come up with techniques that you can work with a large neural network, but you have ways of designing the neural network in such a way by, for example, increasing depth, using regularization, using various types of tricks so that you generalize better on the unseen data. So there are some key issues here. One is, how do you detect overfitting? So because the error on the test data can be caused by several reasons. So for example, it could be caused by bias, it could be caused by noise, it could be caused by poor convergence. So often what happens is that overfitting shows up as a large gap between the in sample, let's say your training data accuracy, and the out of sample accuracy. And when you have this situation, when the gap between the training data and test data accuracy is high, your first solution is to collect more data. But the problem is that more data might not always be available. So in this chapter and the series of lectures, we discuss several techniques to improve generalization neural networks when it's not always feasible to collect more data. So there are several key techniques to improve generalization. For example, we have penalty-based regularization. We have constraints like shared parameters. We can use ensemble methods like dropouts, and we can also add noise or stochasticity to input or hidden units. And we will discuss several of these methods for improving generalization in upcoming lectures.